In this lesson video, we'll continue our exploration into the world of magnetism. And so today we'll look at what the magnetic field is of a long, straight, current-carrying conductor. In other words, if you take just a long wire and you push a current through, what is going to be the magnetic field that results? So that by the end of this lesson, you should be able to describe the magnetic field from an infinitely long, straight, current-carrying conductor. We'll often just call it a current-carrying wire or just a wire. And that you should be able to use the superposition principle to determine the magnetic field vector, both direction and magnitude, from two or more current-carrying wires. Now, we'll start our exploration by a demo that I'll show, a video that shows what happens if you put a set of compasses right next to a current-carrying wire.
I have a wire that goes through a piece of cardboard here, and I've got it surrounded by little tiny compasses. They're all pointing generally this direction. And I'm going to run current through the wire that will be coming up the wire this way from underneath. So based on the right-hand rule, there should be a magnetic field around this wire. In which direction? Let's find out. So I'm going to clip this on now. So it looks like all of the arrows are tending to go around in a counterclockwise fashion from this perspective. I'll turn the current back off. Now I'm going to reverse the current and run it the other direction. So in this case, the current will be flowing down the wire through the cardboard. And let's see what direction the field is there. And now they all seem to be pointing in a clockwise fashion around the wire. The farther I get from the wire, the weaker the field seems to get. I didn't quite line up as quickly or prominently. I'll pull them back a little farther. So they're all being influenced by the Earth's magnetic field there. And they're not all pointing perpendicular to the wire anymore. They're being more greatly influenced by the Earth's field. This one was having a real hard time deciding, is the Earth's field stronger or is this one stronger due to the wire? Let's do a little farther out. There we are. One more try. Kind of a tepid response from a few of them. This one ended up pointing that way. The Earth's field is pointing this way. The wire is trying to point the field that way, and I end up getting some sort of strange component that ends up pointing away from the wire. It's trying to hook around, but it's not doing a real good job. So the field strength drops off dramatically with distance. We'll have to determine mathematically if it drops off as 1 over r squared or 1 over r or some other relationship. But it's definitely stronger close to the wire. The magnetic field around a current-carrying wire.
So as the video very clearly shows, once you switch on the current, all the compass needles reorient themselves and actually form a circle around that wire. And so that suggests that the magnetic field that's caused by the current in that wire, so it suggests first of all that there is a magnetic field produced by that current in that wire because the magnets align themselves again to the north once we switch off the current. So the current definitely produces a magnetic field, but also that magnetic field is in the form of a circular loop around that wire. You can also visualize the same magnetic field by using iron filings, as we've done here. And so again, what you see is that the magnetic field forms these circular loops around that wire, so centered around that wire. So when you look down on, say, in this case, a piece of paper with a wire through, we have to make some conventions about describing our three-dimensional perspective. And we've encountered this before, just wanted to review this here. So we're going to make the convention that if we have a current that's coming out of the page, in this case, we'll denote it by this dot as we do right here. Okay, so that means that there's a current coming out of the page. If we're talking about the current going into the page, we'll actually mark this with a cross like that. So that's a current going down into the page. This is a current coming upwards the page. And so already here, what you see is an indication of what the magnetic fields look like for currents. If the current is an upward current coming out of the page, then we see that the magnetic field follows these counterclockwise loops. If it's a downward current, it's clockwise loops. And so you can do all sorts of experiments, and essentially what you find is that, yes, currents from a wire do produce magnetic fields, and they do produce them in the form of circular loops that are centered on the wire. The direction of the magnetic field depends on the direction of the current, as we've just shown. And actually, in the next slide, we'll come up with a handy right-hand rule to make sure you get your directions right as well. We notice that if we increase the current, this results in a stronger magnetic field. And if we go further away from the wire, the strength of the magnetic field actually decreases. And so we can summarize all these experimental findings with like this equation. So the field strength B equals mu naught times I divided by 2 pi r. And so mu naught is a constant, it's new constant, it's 4 pi times 10 to the minus 7. And the units are Tesla meter per ampere. So we'll see where that comes from. And that constant is called the magnetic permeability in vacuum. So that's different from epsilon naught that we used for electrostatics. This is magnetic permeability in vacuum. So let's look at that right-hand rule to describe the direction of the magnetic fields here. And so here's what you should be looking at. So we've seen that around our wire, we have these iron filings that show these circular loops. We've shown that if the current is going up, so out of the page, then we have counterclockwise magnetic fields. If the current is going into the page, we actually have clockwise magnetic fields. So a simple way to remember this is this right-hand rule. So if you grab a wire, now carefully, don't do this in real life. Don't grab a live wire with a current going through. But if you grab that wire with your thumb pointing in the direction of the current, as indicated here, so an upward current here, then your fingers will actually curl in the direction of that magnetic field. And so you see, if you look from above here, what you see is an upward current coming out of the page, and you see counterclockwise magnetic fields. If the current would be going into the page, then you'd have to turn your hand, so your thumb would be pointing down, and the magnetic field lines would actually point in a clockwise fashion. And so that's a very easy way to essentially figure out what the direction is of the magnetic fields. And so the circles that are shown here are magnetic field lines. And so remember, magnetic field is a vector field. So at any point, the actual magnetic field vector is tangential to these magnetic field lines. And so the magnetic field, in this case, at these four corners, is essentially each time perpendicular to the other one. So if you're thinking back about electric fields, we've also calculated what the electric field is of an infinite wire. And we also found that the electric field decreases by 1 over r, where r is the distance to the wire. So this may actually give you the impression that the electric fields and the magnetic fields are quite similar, and that's not true. So just wanted to clarify that here. So if you look at the electric field for an infinitely long line of charge, so the equation that we found was this: the electric field strength is 2k lambda over r, where lambda is the charge density. Okay, and so you can draw the electric field, and so here's some art by Dr. Wong. You can draw the electric field like this. So you have your line of charge. This is not a neutral wire. This is now a charged wire that's producing electric field. Now the electric field strength drops off with 1 over r, but the electric field vector is pointing away from that line of charge. Okay, keep that in mind, because if you now compare to an infinitely long wire that has a current I, that will now produce magnetic fields. The magnetic field strength also falls off as 1 over R. However, if you draw the situation, it's something quite different, right? So now we have our wire where a current is going through, and so current are moving charges. But so what that means is each time you add a charge, say, on the lower part of the wire here, another charge pops out on the top. So essentially your wire is electrically neutral. It's not charged. And your magnetic field, even though it decreases in strength by 1 over R, just like the electric field, the magnetic fields are actually circular loops around your wire. Very different from these radially outward pointing field lines. So make sure that you don't confuse those two. They are very different vector fields, the electric field and the magnetic fields. So now that we know what the magnetic field is that's produced by a current carrying wire, we can actually look at an example in the series of how physics can save your life. So here's the example. You and a friend get lost while hiking. So your friend pulls out a magnetic compass to get reoriented. However, you are standing right under a power line carrying 1.5 kiloamperes toward magnetic north. It is 10 meters above the compass. The horizontal component of the Earth's field at your latitude points northward and has a magnitude of 0.24 Gauss. Will the compass help you find your way, or will you be lost forever and never get out of the woods? Give it a try and post a solution in a separate video. Here's another example more in the medical field. An insulin pump can be affected by a static magnetic field of 0.2 millitesla. So that's a fairly small magnetic field. How close can an insulin pump wearer come to a long straight wire carrying a current of 20 amperes? So here too, give it a try. Current going down here, for instance, here's a point P. What is going to be the minimum distance that a insulin pump wearer can be to this wire to be safe? Here's another example, coaxial wires. You certainly have some of those in your home right now. So in a coaxial wire, you have essentially two conductors. One is the central conductor here that carries an upward current. Then there's typically some insulating material like this white stuff here. And then there's a second conductor outside there that carries a current that's going in the opposite direction. And both currents are the same magnitude. And so the question is to calculate the B field right here around this cylinder and also around the outer cylinder. And so this kind of brings us to superposition. Magnetic fields obey the superposition principle, which means that the net magnetic field at any given point in space can be obtained by the vector sum of the individual contributing fields. And so here's an example. So suppose that you have two current carrying wires that are a distance 2d apart on the y-axis here. And so in both cases, the current is coming out of the page. And suppose that you want to calculate the magnetic field at point B. And so here's the question: what is the direction of the field at point B, and what is the magnitude of the field at point B? So give it a try yourself, and then you can look at the video with the solution. And so once you've done that, so the solution you find is that at point B, the magnetic field is actually pointing straight up. And now, of course, if you consider magnetic fields, the closer you are to one of these wires, the closer that distance R is. So that means that the magnetic field due to that particular wire will be much stronger than the field due to the other wire. So if you're close to either of the wire, the magnetic field of that single wire will dominate. As you get further away from both wires, you'll actually see that both fields start contributing. And so here's an example of what these magnetic field lines would look like for these two wires around here. So again, close to the wire, you just find regular circular loops that are the magnetic field lines. As you go further away, you actually see that you get some superposition of those two fields.